Hello and welcome back. We will continue our discussion on statistical learning theory. So, before we move ahead, I just wanted to do a small recap of where we are with respect to our discussions, and then take the next step forward in the lecture. So far in statistical learning theory, we have seen the following. So, we have a data set, and from that data set we get a classifier, and the goal was to study the following quantity, which is rs of hs minus r star, where just to recall, rs of hs is training error and r star is the base error. And why do we care about this quantity? Because training error is computable from data. Of course, your algorithm learns a classifier and then you can see how many mistakes the classifier makes on your training set. That is your training error, which is computable from data, whereas the base error is not computable and that is the error achieved by the best possible classifier for the given distribution. And we want to see how good is our classifier performing with respect to the base error, right. And we said that this can be broken down into three parts, which is rs of hs minus rd of hs. This is part 1, and I will talk about this in a minute, plus rd of hs, let me first write it down, minus rd of script h plus rd of script h minus r star. So, basically I am adding and subtracting terms, so it is exactly equal to whatever I had earlier. So, this is the difference between train error of the classifier learned minus the test error of the classifier learned. When there is a d here, it means that the error with respect to the underlying distribution, we know that. So, this is what we were calling as generalization error. This is the generalization error, and this is the difference between the test error of the classifier learnt and the test error of the best possible classifier in the hypothesis class in which we are searching, and this is what is called as estimation error. And the third one is the difference between the error of the best possible classifier in our hypothesis class from which we are learning, and the base error, which is over all possible hypotheses. This is the base error. No, sorry, this is the, so this is the approximation error. So, this is how much we lose by approximating the space of all classifiers by the script h, right. So, the hypothesis class from which we are learning. So, that is the approximation error. So, this is the first thing that we saw earlier, and the second thing is that, okay, so this is how we want to break down the quantity of interest into meaningful parts. So, now what do we know about each of these parts? Well, so far in this course we have been looking at the first part of this, which is the generalization error, and with respect to generalization error, we have the following results so far. So, when you have a finite hypothesis class, maybe I will use a different color, finite hypothesis class, let us call this class H, such that H is less than infinity, cardinality of H is less than infinity, and under this setting, that is, you only have a bunch of H1, H2, H3 till Hk, finite set of hypotheses. We argued that if the number of data points that we have is greater than something like 1 over epsilon squared log of cardinality of H divided by delta, then something interesting happens. What happens? Well, the probability that the train error of the classifier learnt and the test error of the classifier learnt being greater than, the difference being greater than epsilon, is at most delta. And this is good because this is kind of telling me that no matter what algorithm I use, and that is the key point, no matter what algorithm I use, my algorithm is going to pick some classifier, and if I have enough data, which is 1 by epsilon squared log cardinality of h by delta, then I am guaranteed that with enough data, whatever the algorithm that I have, the algorithm will choose a HS, and the train error and the test error of the HS would be close to each other, right. So, meaning would be close to each other with high probability, or deviate by a factor more than epsilon, by a value more than epsilon is at most delta. So, this is the first thing that we saw. So, this is a sample complexity result. That is the first thing we saw. But then we said that, well, we do not care about finite hypothesis classes, what really matters is infinite hypothesis class, and then we looked at infinite hypothesis class. H, so which means that H equals infinity, but then we said that, well, H can be infinity, but the VC dimension of our hypothesis class, let us say some D is less than infinity, that is infinite hypothesis class with finite VC dimension. That's the class that that we were looking at. When you have such a class, hypothesis class from which you are learning, then what can we say? Well, last time we proved that even in this case uniform convergence, we did not prove, I mean, I argued that even in this case uniform convergence will hold. And if you want a sample complexity result, then you will get something of this form. So, if n is greater than or equal to, or rather let me say, if n is order of, without worrying about constants too much, I think even in this one, I think it should be 1 by 2 epsilon squared, but I am not really worrying about the constants so much here. I will put this in order notation, maybe here as well I will call this an order without worrying about the constant notation. So, this is something like d log 1 over epsilon plus log 1 over delta pi epsilon squared. So, then the same thing holds, the train error and the test error deviating significantly happens with very small probability. So, here just to confirm that this D is the VC dimension of H. So, this is again saying that, you know, when you have infinite hypothesis class, you still have a similar kind of result like your finite hypothesis class. The dependence on the cardinality of H kind of gets replaced by, you know, the log of the cardinality of H kind of gets replaced by D, right. So, in this case, so what we have is D log 1 by epsilon plus log 1 by delta. So, there is some extra term that comes here. That is because note that in the finite hypothesis case, the Hofting bound would give something like cardinality of H times e to the minus 2 n epsilon squared, if you remember the right hand side of the Hofting bound. Here it would be cardinality of, I mean, VC dimension of H will dictate the, you know, effective number of classifiers. So, it is going to be something like n power d, or and I mean, if you do a nuanced analysis, you would get something like n divided by d power d into e power minus 2 n epsilon squared, and then, you know, you can arrive at something of this form, right. So, but let me not do that. All I am saying is that, you know, we still have, you know, good generalization even in an infinite hypothesis class, as long as the VC dimension is finite, right. So, that is where we are, right. So, basically what we are saying is that VC dimension, if you know that you are learning from a hypothesis class with finite VC dimension, then you are guaranteed that, you know, if you have enough samples, no matter which hypothesis your algorithm picks, that is the power of uniform convergence, right. So, no matter how my algorithm picks a hypothesis, I am guaranteed that the train error of this hypothesis and the test error of this hypothesis will be close to each other. That is all we are saying, right. So, we are not saying the train error will be low or the test error will be low. That is not what we are saying. What we are saying is that this difference is going to be small, is what we are saying. So, for example, you might have two different hypotheses, one which is performing good on the training data, which means that, let us say, it has only 0.1 train error, right. So, let us just to illustrate this point a little bit more carefully. So, let us say this is the 0 1 line, and let us say you have a data set S and you have two algorithms A1 and A2. You give your training data to both these algorithms. This algorithm produces, let us say, H1, this algorithm produces H2. Both of them depend on the same training data, right? So, it is the same training data given to two different algorithms. I get two different answers. Maybe one is a good algorithm, one is a not so good algorithm. So, what do I mean by good algorithm? So, if I measure the training error, let us say, of H1, I get maybe the training error is 0.1, okay. And maybe if I measure the training error of H2, which is a not so good algorithm, it is not really exploiting any structure in data or anything of that sort. Maybe the training error is 0.45. These are just numbers I am cooking up. So, just to illustrate that, I mean, if the training error is 0.45, it means that 45% of the training data is misclassified by this classifier H2, and that is not a great classifier, right. So, even if you make a lot of training mistakes. But what is this saying, right? So, if you had enough data points, then these numbers are reflecting the test error that you would get if you use these classifiers for testing. What does that mean? That means that, let us say, epsilon, for in this case, let us say we set an epsilon as 0.05, then that means that in this region of 0.1 plus 0.05, which is 0.15, and 0.1 minus 0.05, which is 0.05. So, the same interval for this would be 0.45 plus 0.05, which is 0.5, and 0.45 minus 0.05, which is 0.4. What are we essentially saying here is that the so the test error is going to lie in this interval for H1 and is going to lie in this interval for H2, right. So, for example, the test error of maybe it's a different color. Maybe the test error of H1 is 0.13, right. So, this might be RD of H1, right. So, 0.1 is of course RS of H1, 0.13 might be RD of H1, right. So, similarly, in this case I might get RD of H2 is 0.42 perhaps. Of course, 0.5 is RS of H2. What is this telling me is that, I mean, of course, all these happens with very high probability. So, I am assuming that it is in this range, but with the caveat that all the statements I am making are with high probability, not absolute truth, because simply because you might be very, very unlucky and you might get a data set which is not really representative of the true distribution at all, which means that the data set itself is a very, very low probable event that you saw a data set like this. And so, if you learn from that, well, you are not going to have, I mean, when you are testing, you are going to get something which is more probable from that from the true distribution. And because you learned something which is very, very less probable, you would have not really captured the nuances of the distribution itself. And so, your trainer and test error might be far apart, but that is a low probability event, right. So, for example, it might happen that if I had a bad data and I learned using algorithm 1, my train error might be 0.1, but my test error might be 0.75, could be, right. So, I am saying, but that for that to happen, for such a big difference between train and test error to happen, I should have gotten really, really unlucky, which means that such an event happens with probability less than or equal to delta. Let us say delta is 0.01, which means that 99% of the time I am going to be in this shaded region, the test error is going to be in this shaded region. So, okay, so that is one thing, but assume that the test error is in this shaded region, then what are we saying is that now we are not commenting on how good is our train error or test error, right. So, that is not what generalization error is saying. Generalization error is just telling us that, well, how good is the train error a reflection of the test error. When I say, it is not saying anything in absolute sense, right. So, 0.1 is a better, I mean 0.13 is a better test error than 0.42, that is obvious. right. So, because you don't during test time you want to make as less mistakes as possible, right. So, the chance of going wrong should be less. So, you would prefer classifier H1 over H2 in this case. But if our algorithm picks H2, let us say I do not know, I mean the algorithm gives me only one classifier and let us say that was H2, then the only statement I am so far I am able to make is that, well, I saw the training error and the training error was 0.45 and I know that the test error, if I use this algorithm, sorry, if I use this classifier for my test data, all I can say is that the test error is going to be somewhere between 0.4 and 0.5 with very high chance, which means that I am still going to make 40 to 50% mistakes, right. So, now, this is the level at which we have reached so far, right. So, all we are saying is that no matter which classifier your algorithm picks, its train error and test error are close to each other. We are not making an absolute statement saying that the train error of the classifier HS is small. We cannot say that, because why is that? Simply because we have not commented anything about the algorithm itself. If I have to make a statement saying that the train error is going to be small, or with respect to whatever best that you can do in this hypothesis class or something like that, then I should specify an algorithm. So far we have not specified an algorithm at all. So, without specifying an algorithm, we cannot really say in absolute sense how good our train error will be, right. So, that has not happened yet. So, that's something to keep in mind. So, this is just the generalization error. Okay. So, what then should we do? So, okay, so we saw that we kind of have a handle on this generalization error.